The second part of travelling waves, part of the waves topic. This is the second section of waves and the second part of the second section. And having already looked at basic waves terms such as wavelength, frequency, period, speed of waves, and the difference between transverse and longitudinal waves, we're now going to focus on a particular application, so to speak, that of electromagnetic waves. And the most common electromagnetic wave is light, which might lead us to the question, what is light? Now, I think this is fascinating and it's fundamental to our current understanding of how our universe works. Because light is a form of electromagnetic radiation. What does that mean? It means that there are these things called fields, these things called the electric and magnetic fields, and that any form of electromagnetic radiation is a disturbance in these fields. But what does that mean? Well, the reason I'm chosen as an image here, the bottom of a underwater or a pool, is because you can think of these fields as something that surrounds us, that occupies all the volume of the universe. In fact, one way of thinking of it, a sort of more mathematical approach, is to imagine, if you can, a grid, a network of points stretching off to infinity in all directions. Each of these points represents a value. It has a number associated with it. In fact, for the electric and magnetic fields, it has a number and a direction, which makes it a vector. So there's this grid of points, each of which can have a vector associated with it. And these vectors can change over time. So this is an evolving system. And the way that one number changes, one vector changes, it will change the vector next to it. They will propagate, they will have an effect. And if you play the animation over time, you will see changes and ripples going throughout the entire network. All of this is described mathematically. The vectors and how they change can be described by equations. And if we take a slice through this path, then we will be able to see, well, this is a 3D visualization of what I'm trying to show you. Here we can see different vectors spread out through space, and this is like a freeze frame, but if we could press play, then we could see these vectors change over time. For electromagnetic waves, in the electromagnetic field, we can think of there being two associated vectors. They are the B field, which represents the magnetic field, and the E or electric field. And when we have electromagnetic radiation created, which is generally done by moving charges, by electrons, for example, moving, then they will, as they move, create ripples in the B field, and the B field creates ripples in the electric field. And so we have these two associated vectors, and you can see how it changes over space as a wave goes past, and you can also see that it's a transverse wave. This animation shows that process. So here you can see, if we look at the vector at one point, just this point here, how over time the B vector is changing and how the associated E or electric vector is also changing, and how they change as the wave passes in a certain direction along, in this case, parallel to the y-axis. So now you've got an idea of what an electromagnetic field is and what electromagnetic radiation is. Then you just imagine that the space around you, as you sit watching this video, as I make this video, that entire space is filled with a sea of electromagnetic fields. So it's not like you have a field with just one wave propagating through it. Instead, you have thousands, millions of waves all adding up at the same time with a vast range of wavelengths. Different wavelengths corresponding to different parts of what we call the electromagnetic spectrum. And visible light is just a fraction of those wavelengths. It's those wavelengths that we can perceive via our eyes. So all these waves, as I say, as I sit here making this video, are all adding up, and they all come in and they enter your eyes, because your eyes have evolved to make use of a small part of that spectrum. Your eyes consist of light-sensitive detectors, rods and cones. Rods work in black and white light. They work in black and white only, but they work in faint light, whereas cones, you have three types of cones called S, M and L cones, and they are able to detect the different colours, approximately adding up to the sort of red, green and blue parts of the spectrum. As I said, visible light is just a small part of the electromagnetic spectrum. Notice how this scale here is a logarithmic scale. It goes up in factors of 10. And similarly, you have the wavelength. And these wavelength and these frequencies are related by the equation C equals F lambda. And if you multiply F and lambda, the frequency and the wavelength together, you will always come up with the same value of C, the speed of light, approximately 3 times 10 to the 8 meters per second. All electromagnetic waves propagate at the speed of light. The Earth's atmosphere, it's an interesting chart. It shows you that the Earth's atmosphere is only transparent at some wavelengths. For example, it's transparent, obviously, in the visible, but most of this part of the spectrum, the ultraviolet and the X-ray, it's quite opaque. Similarly, for the microwave region of the spectrum, microwave radiation only travels a relatively limited distance through atmosphere. Here is another version of the same spectrum. We have the visible spectrum, just one small part between this increasing wavelength and increasing frequency in the other direction. Something you should remember, or try to remember, one of those little numbers and facts, is that the wavelength range of visible light is about 400 nanometers to about 700 nanometers. And you can easily calculate what the frequency range is, again using this equation. I thought I'd finish with a couple of questions from past IB papers just to illustrate the kind of things you might be given. There aren't, to be honest with you, often very many questions specifically about the electromagnetic spectrum. Here is one from 2009, just a simple multiple choice, which gives you a wavelength, 600 nanometers. Remember, I told you that you should try and remember that visible is from 400 to 700. 600 is about here, the orange part of the spectrum, so that's visible light. And the second question, it's actually from one of the options in 2011. What are 2 properties common to all electromagnetic waves? I think this is a good question. It's one that I remember a lot of students getting wrong because they gave answers that were common to waves, all waves. So they were talking about properties such as reflection and refraction. But all waves do that. And the question was specific, what is common to all electromagnetic waves? And the best answer there is that all electromagnetic waves travel at the speed of light, and all electromagnetic waves are transverse waves. Another possible answer was that they can be polarized, which is something that only transverse waves can do, and we will look at shortly. So I hope this has given you an idea about the nature of electromagnetic waves, and just a reminder about this equation, C equals F lambda. Thank you.